ここキャンプできそうだから。
In quantum mechanics, there's a common scale of discreteness, right, which is given by the Planck scale, obviously. What the Planck scale is an action. What is an action? Here is an action. I need a pendulum. Here's a pendulum. Okay. So this oscillates, and I make a measurement. I measure as 20 centimeters the oscillation, okay, plus or minus 2. So the amplitude is the ratio of the energy, so I measure the energy. I've measured the energy is between a minimum and a maximum. So what is it that I still don't know about the system? Information. There are many possible ways this can move. There are many possible states of motion that are compatible with my measurements. I know how to characterize them. They are the region of phase space which are between energy E1 and E2. How many they are? Well, just the area of this region. The area of this region, anybody can do this calculation, is this thing here. But wait a moment. The world is quantum mechanical. Ah, yeah, I forgot. So, in fact, the energy spectrum is discrete. So how many possible orthogonal states there are compatible with my measurement? Oh, well, this is the spectrum of the energy. Anybody know how to do this calculation? This is a number. So there's a discrete number of alternatives. Number of alternatives, how do I measure it? Information. That's what is, okay? So there is a discrete information. There is an information which is missing when I do this measurement of the amplitude, which is finite, okay? And which is exactly A divided by H. So what is quantum mechanics telling me? Quantum mechanics is telling me that every region of phase space in fact contains less information than this apparently infinity quantity measured by energy, by action, and that there is a unit of information which is 1 h bar of action. So quantum mechanics tells me that I can translate action into information cleanly, and it has a clean geometry. This is completely general. I did it for harmonic oscillator, but of course any system with any number of degrees of freedom is the same. So the amount of information which is in a finite region of space-time per any system is finite. The finite region of space-time is a finite number, and the scale of it is given by h. And that's the first postulate of relation of quantum mechanics, right? Finiteness of the information that contains a system. The same is true in quantum field theory. So discreteness, I think, is a defining property of quantum mechanics. It's the core of quantum mechanics. The scale is given by h. This is what I just said. Quantum discreteness implies that information is never sharper than h bar. So information in nature is discrete. It's not an obvious fact, because it's not measured by action. It's discrete, so it's not a tautology, this one. True fact. The fact of nature. And so I can better use h bar as my unit of action. It's like the speed of light, right? It's once I have a preferred velocity, I can just adapt. I can take c equal 1, I can take h equal 1. It's the same story. There is a maximum velocity. Here there is a minimum amount of information in a system. So what is quantum mechanics? I think that quantum mechanics is the physical discovery of the existence of a physical limit in information transfer processes. Thanks. And I think that an interpretation that is blind to discreteness is just missing something about quantum mechanics. It's missing something core about quantum mechanics. So it's time to close. I have two final slides just to go back to cosmology. Again, tomorrow I will bring gravity in. This will be much more concrete. I will be much more physics and less foundational. And I will tell how this point of view is useful for doing quantum gravity. In fact, I think it's the only one we can do quantum gravity, unless we go to asymptotic to infinity, which is nonsense for a relativist. And I will show how it's useful in cosmology, and in fact how it's been used in cosmology by others, not by me, to go to give descriptions about early cosmology, the physics of early cosmology, of course, tentative description of physics of early cosmology, and do predictions. So let me close by the relevance for cosmology. First of all, let me repeat. Cosmology describes real facts, nothing idealistic, about a few large-scale degrees of freedom of the world and the way they affect which is the majority of the degrees of freedom, including us, our telescope, and everything else. The observer in cosmology is totally unproblematic. Is not part of the degrees of freedom. I'm observer, you're observer, classical order observer. There's nothing idealistic, nothing Wigner, nothing consciousness of that. It's the standard observer. It's just the object whose dynamic is affected by the large-scale degrees of the universe and so on and so forth. And the dynamic of this large-scale degrees of freedom is semi-classical most of the time, but is influenced by quantum corrections, of course, in some regimes, early universe, typically. In those regimes, I have to use quantum mechanics because space-time will be... In fact, I will have to use quantum gravity because space-time is not defined, so I will have to compute the way this non-space-time region affects the rest. Okay? And this will be possible to do with if you have a theory of quantum gravity, of course. So I don't think there is any problem about foundation of quantum mechanics that touches cosmology, nor there is any problem about cosmology that touches the foundation of quantum mechanics. Perhaps inflation helps us to understand entropy. If I understand it better, I will be happy. This will be perfectly fine. I'm not saying that two things cannot be useful for one another. This is about cosmology. What about tautology? Because I said there's a legitimate problem, which is tautology. Well, quantum tautology, again, is a problem in the philosophy and in the foundation of quantum mechanics. A legitimate problem with nothing to do with physical cosmology. Is the description of the manner in which the totality of the existence of physical things interact, producing real events. So therefore, the problem of quantum tautology splits in two parts. One is how one part interacts with another one, and I've just told you this is quantum mechanics. Quantum mechanics tells how things interact with another one. Okay? The velocity of this is relative to the velocity of that. So this fact is relative to this fact here. The other part, which people may legitimately ask, is how the whole interacts with something else. Everything with respect to nothing. I think that the interaction of the whole with something else is something non-existing because there's no something else. So I don't think there's any problem here either. Thank you.
오늘 뭐 싸우고 그러고 가요.
So, Carlo, I'd like to ask you about what you said about consistency. You got the system, an observer looking at the system, and then a bigger observer looking at the observer. Let me ask you, let me maybe give an example. When you were invited to come here to give a lecture, let's say you weren't sure whether to accept or not, and you decided, look, why don't I just measure the spin of a particle in the lab? If it comes out up, I'll accept. If it comes out down, I won't accept, okay? Now, presumably in some standard quantum mechanics description, there's a wave function where, in a sense, in one branch, you accept, you're here, you give the talk, and the electron has spin up, and there's the other branch where it's the opposite, okay? However you want to interpret that wave function. Now, it sounds as if you're saying that, well, relative to the electron with spin up, it's a fact that you're here and gave the talk. Something like that. But let me ask the further question, which I really want to get to. Let us say now that some super observer, it might be some advanced being that exists now or in the future with some super technology, performs what we would call an interference experiment between these two branches. Now, presumably you would say that relative to this super observer, there is no fact of the matter as to whether you gave a talk here or not, because for him the two realities, or however you want to put it, are interfering. There isn't one or the other, there's an and. Now, so it seems like the logical conclusion of this that you would say that it could be that for other intelligent beings now or in the future, it is not a fact that you are here today giving this lecture. And would you agree with that? And if you do, does it not make you feel uncomfortable?
The answer to the first question is yes. The answer to the second question is no.
Well, Carlo, what can I say? You've managed to jump through many hoops, which I doubt it could be jumped through. So, but here's, I think, what is the central objection to me in the way that you're phrasing this. I would say that physics is often bound up with schematic descriptions, and surely is not concerned with tautology, with absolutely everything that there is, but is concerned with relevant, let's look at large degrees of freedom of the universe, and is concerned with questions of measurement and observation, and forgets about all of the rest of the stuff in the universe, goes to a highly schematized description which just concerns a measuring apparatus and large-scale degrees of freedom of the universe, and attempts to model those as a dynamical system and extract meaningful information. It seems to me that this is very much historically how fundamental physics has worked. Now, in that framework, it seems to me the fact that one has omitted certain, almost all of the universe is only focusing on those skeletal fragments of the universe is entirely appropriate, and yet carries with it, because we are dealing with the entire universe, the suggestion that to bring in more stuff would be irrelevant. It would be irrelevant vis-a-vis an understanding of how these large-scale degrees of freedom interact with the measuring apparatus. It's just not going to impact upon that evolution. Now, if you do that within conventional quantum mechanics, it seems to me it is illegitimate to invoke an external observer. You do need some definite rules as to how that interaction is to proceed, and I don't see that your framework provides them.
I think, translated in the language that you like, what I'm saying is that, look, with the universe, I'm in a branch, forget the other branches. In this branch, there is the universe plus my apparatus. I have some physics that describe the interactions between my telescope and the scale factor, because
I have the unitary evolution of the state. I have these definite rules. What is your definite rules?
The definite rules are the one I read in is Bohr, is one I read. So what I'm saying is that take
an external observer.
That's right. What I'm saying is take Bohr, quantum mechanics, the one which and instead of thinking that there is a special object which is observer, because it's a Wigner mind, because it's macroscopic, because it's classical, just democratize Bohr. With respect to any system, you could play I think the quantum mechanics is about relations in the system, one which Bohr system and one which Bohr would call the classical system, which is the thing being affected about. But what is going on is fact of the matter that happens in this interaction. So I'm not doing anything strange. I'm saying, if you want to describe the universe, you have in the quantum universe, you have in the space for these large degrees of freedom, a set of observables for these large degrees of freedom, which describe what? Describe the physical interaction between these large degrees of freedom and my telescope. For instance, I have a telescope that measures the temperature of the cosmic background radiation. So it spins a number. So the fact of the matter is a number which I interpret as a property of the system, and I want to say this is the number. So I want to just talk in terms of actuality, not in terms. It's a choice, but I think it's a more useful choice. It's like in David Lewis. I can say that all possible worlds exist and one is actual. That's fine. I mean, I cannot convince David Lewis that this is the way to go. In fact, it's thanks to you that I got into David Lewis. Or I can say the actual world is what I want to call real, what I will call existence, and the other I'm happy with modality, and what I don't understand about modality is just happy with that. So I'm happy, like most of the philosophers, to not follow Lewis and just leave the rest of the branches, the rest of the possible worlds in a lesser ontologically heavy status. Same thing I would like to do with the other branches. What happened.
Thank you. I really enjoyed your talk. I have two questions. One conceptual first, and then a technical one. Conceptually, my sense, comparing your view and my view, I know we've been invited here to disagree with each other, but my sense is that we actually don't disagree on anything of substance, merely of emphasis. So if we look, for example, at that other version of Carlo Rovelli who decided not to come to the meeting, or maybe another observer who lives on a galaxy outside our Hubble volume, or even some guy who lives on Andromeda, I completely agree with you that it's not useful for him to factor us into his density matrix, because we won't have any effect on him for 3 million years when he'll be dead. But first of all, I think it would be a little bit rude for him to say that we don't exist just because he doesn't find us useful for him. And second, I didn't go into physics just because I wanted to do only useful things. Sure, it's useful, but the main reason I'm doing physics is because I love it, and I find it just super interesting to try to understand it a little bit better, what's really out there, and my place in it. So my first question is just to what extent you would agree with the fact that it's just that you're simply not interested in so much in that question of what's really out there if it's useless, which I respect, And the second question I have is the technical one, because you said that you don't believe that just a wave function and a Hamiltonian operator is enough structure to derive everything that we observe. So I'm curious to hear what additional structure you think is necessary, whether you think we also need a lot of what I call many words, a lot of Niels Bohr kind of stuff, whether you need some sort of semi-classical world and apparatus or whatever as an extra structure, or whether you think the only extra structure we need is a more mathematical structure. Do we need 2 more operators or infinitely many more? Or what do you think we need in addition?
Okay, thanks for the nice comment. The two questions. The first is the answer to the first is this. I think that the difference is only a difference in emphasis. I agree. I would add, however, that the emphasis is not just on me being less interested in the other branches, but it's also in the fact that I would insist that more structure is needed than just. And this takes me to the second question. So what